47 years ago, humanity threw a bottle into the cosmic ocean. We launched two spacecraft, Voyager 1 and Voyager 2, on trajectories that would take them past the outer planets and eventually into interstellar space. We expected them to send back pictures of Jupiter and Saturn, maybe last a few years, then fall silent. Instead, they kept going. And going. Across distances no human-made object had ever travelled, through regions of space we'd only theorised about, into realms where the sun's influence fades and something else begins. And when they crossed the boundary between our solar system and the vast emptiness beyond, they found something. Not what we expected, not what our models predicted, something strange enough that scientists are still trying to understand what it means. The data came back as radio signals, faint whispers travelling for hours across the void. Numbers, measurements, readings from instruments designed in the 1970s, still functioning against all odds in the cold darkness at the edge of everything we've ever known. Those numbers told a story about where our solar system ends and what lies beyond. A story that challenges our understanding of how stars interact with the galaxy. A story that's still being written as the Voyagers continue their journey into the unknown. If you're ready to learn what humanity discovered at the frontier of our cosmic neighbourhood, subscribe and prepare yourself. What you're about to hear changes how we understand our place in the galaxy. We begin. The Voyager missions were conceived during a rare planetary alignment that occurs once every 175 years. In the late 1970s, the outer planets arranged themselves such that a spacecraft could visit multiple worlds using gravity assists, gaining speed at each encounter without burning fuel. NASA seized this opportunity. Voyager 1 launched in September 1977, followed by Voyager 2 2 weeks earlier on a slower trajectory. Both carried identical instrument packages, cameras, spectrometers, magnetometers, plasma detectors, and cosmic ray sensors. And both carried golden records containing sounds and images from Earth. Messages for any intelligence that might someday find them drifting through the galaxy. The primary missions succeeded beyond expectation. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, sending back stunning images and revolutionary data. Voyager 2 visited Jupiter and Saturn, then continued to Uranus in 1986 and Neptune in 1989, completing the first grand tour of the outer solar system. After Neptune, the spacecraft had completed their planned missions. Most expected them to simply continue outward until their power sources died and they fell silent. But mission planners had other ideas. They realized the Voyagers could reach a region no spacecraft had ever explored, the heliopause, the boundary where the sun's influence ends and interstellar space begins. This wasn't just about exploration. It was about understanding fundamental physics. How does a star's wind interact with the interstellar medium? What happens at the boundary between stellar and galactic environments? These questions had profound implications. The sun creates a bubble of influence, a heliosphere, by emitting a constant stream of charged particles called the solar wind. This wind pushes outward in all directions, creating a protective bubble that shields the inner solar system from galactic cosmic rays. But the galaxy has its own environment. The interstellar medium contains gas, dust, magnetic fields, and cosmic rays. These two environments, solar and galactic, must meet somewhere. The boundary between them is the heliopause. No one knew exactly where this boundary was. Estimates ranged from 80 to 120 astronomical units from the Sun. One astronomical unit is the Earth-Sun distance, so we're talking about 80 to 120 times farther from the Sun than Earth. The Voyagers were already racing outward at speeds approaching 60,000 kilometers per hour. They would reach the heliopause eventually if they survived long enough. The question was what they would find when they got there. Scientists predicted a relatively simple structure. The solar wind would push outward until it met sufficient resistance from the interstellar medium to slow down. This slowdown would create a termination shock, a boundary where the supersonic solar wind becomes subsonic. Beyond the shock would be the heliosheath, a region where solar wind continues outward but no longer dominates. Finally, at the heliopause itself, the solar wind would stop completely and interstellar space would begin. Simple, clean, a three-layer structure: solar wind, heliosheath, interstellar space. Reality turned out to be far more complex. Voyager 1 crossed the termination shock in December 2004 at 94 astronomical units from the Sun. The spacecraft's instruments detected a sudden change in the solar wind speed and an increase in magnetic field strength. This matched predictions perfectly. The shock was real, located roughly where models suggested. But then things got weird. As Voyager 1 continued through the Helios heath, it encountered phenomena no one expected. The magnetic field didn't behave as predicted. Cosmic ray intensities varied in strange ways. The plasma environment showed anomalies that didn't fit standard models. Scientists initially attributed these oddities to local variations, temporary fluctuations in an environment we didn't fully understand. But as Voyager continued collecting data year after year, it became clear the anomalies were systematic. The Helios sheath was more complex and dynamic than anyone imagined. Then in August 2012, Voyager 1's instruments detected dramatic changes. The solar wind particles dropped to nearly zero. Galactic cosmic rays increased dramatically. The magnetic field strength changed. After analysing the data for months, NASA announced in September 2013 that Voyager 1 had crossed the heliopause. It had left the solar system and entered interstellar space. But here's the strange part. The magnetic field direction didn't change. This was unexpected. Models predicted that the Sun's magnetic field, which dominates the heliosphere, should have a different orientation than the galactic magnetic field in the interstellar medium. Crossing the heliopause should have produced a dramatic shift in magnetic field direction. It didn't happen. The magnetic field Voyager 1, measured in interstellar space, pointed in nearly the same direction as in the Helios heath. Either the models were wrong about magnetic field behaviour, or something more complex was happening at the boundary. Voyager 2 crossed the heliopause in November 2018 at a different location and with different instruments still functioning. It measured similar phenomena, dramatic changes in particle populations and cosmic ray intensities, but no corresponding change in magnetic field direction. Two spacecraft, two different crossing locations, same anomalous result. This wasn't a fluke. This was telling us something fundamental about how the heliosphere interacts with the galaxy. The discovery suggested that the Sun's magnetic influence extends beyond the heliopause. The boundary is more permeable than expected, allowing magnetic fields to penetrate from one side to the other. Or perhaps the local interstellar magnetic field happens to align with the Sun's field, a coincidence that seems too convenient to be random. Scientists are still debating what this means. Some propose that the heliopause is not a clean boundary, but a transition zone where solar and galactic influences mix. Others suggest that magnetic reconnection, a process where magnetic field lines break and reconnect, allows solar and interstellar fields to link, creating unexpected configurations. Whatever the explanation, the Voyagers discovered that the edge of our solar system is not what we thought. It's not a simple boundary separating two distinct regions. It's a complex, dynamic interface where physics operates in ways we're still trying to understand. And that was just the first surprise. As the Voyagers continue their journey deeper into interstellar space, they're finding more phenomena that challenge our understanding of the galaxy we inhabit. Just beyond the heliopause, where interstellar space should be relatively uniform and predictable, both Voyagers encountered something that wasn't supposed to be there. A wall. Not a physical barrier, but a region where hydrogen atoms pile up, creating a density enhancement that scientists are calling the hydrogen wall. This discovery emerged gradually from Voyager data. The spacecraft carry instruments that detect ultraviolet light scattered by hydrogen atoms. In interstellar space, hydrogen should be distributed fairly uniformly, maybe with some variation due to local conditions, but nothing dramatic. Instead, the Voyagers detected a distinct increase in ultraviolet emissions coming from ahead of their trajectory. The signal suggested a concentration of hydrogen atoms somewhere beyond their current position, an enhancement in density that shouldn't exist based on standard models of the interstellar medium. This hydrogen wall appears to be a structure created by the interaction between the heliosphere and the interstellar wind. The galaxy rotates, and our solar system moves through the interstellar medium at roughly 80,000 kilometers per hour. This motion creates a headwind, a flow of interstellar material toward the solar system. When this interstellar wind encounters the heliosphere, it slows down and compresses, Just as air compresses in front of a supersonic aircraft, the slowed material piles up, creating a region of enhanced density ahead of the heliosphere's motion. This makes sense theoretically, but the hydrogen wall appears to be more pronounced and more localized than models predicted. It's not a gradual enhancement, but a relatively sharp transition, almost like a bow shock in fluid dynamics. The implications are significant. If interstellar material piles up in front of moving stellar systems, then every star creates a similar structure as it moves through the galaxy. These hydrogen walls would be ubiquitous, a previously unknown feature of stellar dynamics. This affects how we understand star formation. Young stars often have strong stellar winds that clear out their surroundings. But if they're also creating hydrogen walls ahead of their motion, those walls might affect the distribution of material around them, potentially influencing where and how new planets form. It also affects our understanding of cosmic ray propagation. Cosmic rays are high-energy particles that travel through the galaxy. Their paths are affected by magnetic fields and density variations. If hydrogen walls are common, they might deflect or slow cosmic rays in ways we haven't accounted for. For the Voyagers themselves, the hydrogen wall represents an opportunity and a challenge. An opportunity because passing through it will provide unprecedented data about these structures. A challenge because the enhanced density might increase the risk of collisions with dust particles. Interstellar space isn't empty. It contains gas and dust, albeit in extremely low concentrations. But even a tiny dust grain, when encountered at Voyager's speed, carries enormous kinetic energy. A collision with a sufficiently large particle could damage or destroy the spacecraft. The Voyagers have survived this long partly through luck and partly through careful trajectory planning. They're travelling through what appears to be a relatively clear region of local interstellar space, but the hydrogen wall might be denser, potentially more hazardous. So far, both spacecraft are healthy considering their age. Systems are failing gradually as components wear out and power supplies decline, but the critical instruments, those measuring the interstellar environment, continue functioning. Barring a catastrophic collision, the Voyagers should continue transmitting data for another 5 to 10 years. When they finally fall silent, either from power depletion or component failure, they'll have given us our first direct measurements of the local interstellar medium. The hydrogen wall data is just one piece of a larger puzzle about how stellar systems interact with their galactic environment. But the wall raises questions that the Voyagers alone cannot answer. How large is it? How far does it extend? Does it vary with solar activity? The Voyagers are travelling through one small region of this structure. They can measure its properties along their trajectory, but they can't map its full extent. Other observations supplement Voyager data. Hubble Space Telescope. Ultraviolet measurements have detected similar enhancements around other nearby stars. These observations suggest that hydrogen walls are indeed common, that most stars create such structures as they move through the galaxy. This means our solar system sits inside a kind of bow shock, a wave of compressed, interstellar material pushed ahead of the sun's motion. We're in the wake behind this wave, shielded from some galactic influences by the material piling up in front. This shielding might affect the cosmic ray environment in our solar system. Cosmic rays from certain directions might be partially blocked by the hydrogen wall, creating an asymmetry in cosmic ray arrival directions. Indeed, some observations hint at such asymmetries, though they're subtle and difficult to confirm. The hydrogen wall also contains information about the local interstellar medium's composition and properties. By measuring how material piles up and how it responds to the sun's motion, we learn about the density, temperature, and magnetic structure of our galactic neighbourhood. These parameters matter for long-term thinking about Earth's environment. The solar system moves through the galaxy, passing through regions of varying density and properties. Sometimes we're in dense molecular clouds, sometimes we're in tenuous voids. These variations might affect the cosmic ray flux reaching Earth, potentially influencing climate and biological evolution over millions of years. The hydrogen wall is a temporary feature in cosmic terms. As the solar system continues its orbit around the galaxy, it will eventually move into different regions with different properties. The wall will change character, perhaps disappearing entirely if we enter a particularly dense region where the interstellar medium's pressure overwhelms the sun's influence. But for now, For the epoch in galactic history, when the Voyagers happen to be making their measurements, the hydrogen wall exists. It's a structure created by the specific conditions in our current galactic location, a signature of how our solar system interacts with its surroundings. The discovery highlights how much we still don't know about even our local galactic environment. We can see distant galaxies billions of light years away. We can detect exoplanets around other stars, but we're still discovering basic features of the space immediately surrounding our solar system. The interstellar medium isn't the empty void early astronomers imagined. It's structured, dynamic, responsive to the presence of stars and their winds. The Voyagers have given us our first direct measurements of this environment, revealing complexity we didn't anticipate. As the spacecraft continue their journey, they'll probe deeper into this realm. They'll measure how properties change with distance from the Sun. They'll detect variations over time as solar activity waxes and wanes. They'll encounter structures we can't yet predict, and when their power finally runs out and they fall silent, they'll continue drifting through the galaxy as silent ambassadors of humanity, carrying their golden records, perhaps to be found millions of years from now by beings we can't imagine in regions of space we'll never visit. But the data they've already sent back has transformed our understanding of where our solar system ends and what lies beyond. The hydrogen wall is just one discovery among many that reveal the richness and complexity of the interstellar environment. The magnetic field measurements from the Voyagers have revealed one of the most puzzling aspects of the heliopause crossing. Both spacecraft detected strong magnetic fields in interstellar space, but these fields pointed in unexpected directions and showed strange variations that don't match our models of galactic magnetism. In the heliosphere, the magnetic field is dominated by the Sun. The Sun's magnetic field is carried outward by the solar wind, creating a complex structure that spirals outward like water from a rotating sprinkler. This solar magnetic field should end at the heliopause, replaced by the local interstellar magnetic field. The interstellar field is generated by galactic processes, currents flowing through ionized gas on vast scales, magnetic fields amplified by turbulence and shear, structures shaped by supernova remnants and stellar winds. This field should have a different strength and direction than the solar field. Voyager 1 crossed the heliopause expecting to see a sharp rotation of the magnetic field direction. Models predicted the field should swing from the solar orientation to the interstellar orientation within a relatively short distance, perhaps a few astronomical units. It didn't happen. The magnetic field strength increased as expected when crossing the heliopause, jumping by a factor of 2. But the direction barely changed. The field in interstellar space pointed almost exactly the same direction as the field in the outer Helios heath. Scientists initially thought this might be a local anomaly, a quirk of Voyager 1's specific crossing location. But when Voyager 2 crossed the heliopause 6 years later at a completely different location, it measured the same phenomenon. Strong magnetic field, no directional change. 2 independent measurements, same result. This wasn't coincidence. This was telling us something fundamental about magnetic field structure at the heliopause. One explanation: magnetic reconnection. This is a process where magnetic field lines from different regions connect and exchange energy. If solar and interstellar magnetic fields are reconnecting at the heliopause, they could create a hybrid field structure that combines elements of both. In this scenario, the field lines from the Sun don't simply terminate at the heliopause. Instead, they connect with interstellar field lines, creating extended structures that reach into interstellar space. The Voyagers would then be measuring these connected fields, which retain the solar orientation even beyond the formal boundary. This explanation works mathematically, but it requires very specific conditions. The solar and interstellar fields must have compatible orientations for reconnection to occur efficiently. They must be close to anti-parallel, pointing in nearly opposite directions, for the field lines to connect smoothly. The fact that both Voyagers measured compatible fields at their very different crossing locations suggests either extraordinary coincidence or something more systematic. Perhaps the local interstellar field is oriented favourably for reconnection over large areas. Or perhaps the reconnection process itself aligns the fields in ways we don't yet understand. Another possibility: the heliopause is not a sharp boundary, but an extended transition zone. the magnetic field might gradually rotate from solar to interstellar orientation over a large distance. The Voyagers haven't travelled far enough into interstellar space to see the completion of this rotation. This explanation requires the transition zone to be unexpectedly large, perhaps tens of astronomical units across. Current models don't naturally produce such extended transitions, but modifications to account for turbulence and instabilities might. The magnetic mystery extends beyond just field direction. The field strength also behaves strangely. In interstellar space, the field should be relatively uniform, varying slowly over large distances. Instead, Voyager measurements show significant fluctuations on scales of months to years. These fluctuations might reflect turbulence in the interstellar medium, waves and eddies in the magnetized plasma that fills the space between stars. Or they might indicate that the spacecraft are still in a transition region influenced by the heliosphere, not yet in truly pristine interstellar space. The time variations also show curious patterns. Sometimes the field strength increases, sometimes it decreases. Sometimes it correlates with changes in cosmic ray intensity. Sometimes it doesn't. There's structure in the data, but the structure doesn't match simple theoretical predictions. Some of these variations might be seasonal effects from the heliosphere. Even though the Voyagers have crossed the heliopause, the boundary itself moves. Solar activity varies on an 11-year cycle, and the solar wind strength varies with it. When the solar wind is strong, the heliosphere expands. When it's weak, the heliosphere contracts. This means the heliopause oscillates, moving inward and outward over the solar cycle. The Voyagers might be experiencing multiple crossings as the boundary washes over them, back and forth, creating the variations we observe. Testing this hypothesis requires tracking both Voyager measurements and solar activity over multiple solar cycles. We're beginning to accumulate enough data to see patterns, but definitive conclusions require more time. The magnetic data also affects our understanding of cosmic ray modulation. Cosmic rays are deflected by magnetic fields. The stronger the field, the more deflection. If the interstellar magnetic field near the heliopause is stronger than expected, cosmic rays approaching from certain directions might be deflected more than models predict. This could explain some anomalies in cosmic ray observations. Detectors on Earth and satellites measure cosmic rays from all directions, and the intensity should be roughly uniform. But there are subtle variations, hints of directional asymmetries that don't match simple models. If the local interstellar magnetic field has unexpected structure, it might channel cosmic rays preferentially from certain directions, creating the observed asymmetries. The Voyager magnetic field measurements provide crucial constraints on these models. The magnetic mystery also has implications for other spacecraft. When we eventually send another mission to interstellar space, and we will, whether in decades or centuries, we'll need to know what magnetic environment to expect. The Voyager data suggests it's more complex than we thought, which means future missions need different instruments and measurement strategies. Perhaps most intriguingly, the magnetic measurements hint that the heliosphere might be more connected to the galaxy than we realized. If solar and interstellar magnetic fields are linked through reconnection, then our solar system isn't an isolated bubble. It's magnetically connected to its surroundings, part of a larger galactic magnetic web. This connectivity could allow particles and energy to flow between the heliosphere and the galaxy more easily than expected. It might affect how solar activity influences the local interstellar environment. It might even create pathways for cosmic rays to penetrate deeper into the solar system than they otherwise could. The Voyagers continue measuring the magnetic field as they travel deeper into interstellar space. Each year they move farther from the Sun, sampling regions no spacecraft has visited before. The data accumulates, patterns emerge, and our understanding slowly improves. But the central mystery remains. Why does the magnetic field near the heliopause behave so differently from predictions? We have hypotheses, ideas, possible explanations. We don't yet have definitive answers. Solving this mystery requires more than just Voyager data. It requires understanding magnetic field generation and evolution on galactic scales. It requires better models of how stellar winds interact with the interstellar medium. It requires grappling with physics that's far more complex than the simple diagrams in textbooks suggest. The magnetic field at the edge of our solar system is teaching us that even basic questions about our cosmic environment remain unanswered. We're still explorers in unknown territory, and the Voyagers are our scouts, sending back reports from the frontier. One of the Voyager's primary objectives was measuring cosmic rays, high-energy particles that fill the galaxy. These particles, mostly protons and atomic nuclei, accelerated to near light speed by supernova remnants and other violent events, rain down on the solar system constantly. But the Sun's magnetic field, carried outward by the solar wind, deflects many cosmic rays before they reach the inner solar system. This creates a cosmic ray gradient. Intensity increases as you move farther from the Sun, reaching maximum values in interstellar space where solar influence ends. Scientists predicted that crossing the heliopause would produce a sharp increase in cosmic ray intensity. The Voyagers should suddenly be exposed to the full galactic cosmic ray flux, no longer shielded by the heliosphere. What actually happened was far more interesting. Voyager 1 saw cosmic ray intensity increase dramatically in May 2012, 3 months before the spacecraft officially crossed the heliopause. The intensity jumped by more than 40% in just a few weeks, then stabilised. This seemed to confirm the crossing, suggesting the spacecraft had entered interstellar space. But other indicators disagreed. The magnetic field direction hadn't changed. The plasma environment still looked like Helios Heath, not interstellar space. Something was happening that didn't fit the simple heliopause crossing scenario. Then in July 2012, the cosmic rays dropped back down almost to previous levels. 2 weeks later, they surged again. Up, down, up. The intensity oscillated wildly over the following months. Finally, in August 2012, the cosmic rays reached their highest levels and stayed there. Simultaneously, solar wind particles dropped to zero. This was the true crossing. But what were all those earlier fluctuations? Scientists realized they were seeing something unprecedented. The boundary region near the heliopause is not static. It's dynamic, turbulent, filled with magnetic structures that trap and release cosmic rays in complex patterns. The heliosphere has a magnetic depletion layer near the heliopause where magnetic field lines pile up and create a partial barrier to cosmic rays. This barrier isn't uniform. It has holes, weak spots where cosmic rays can penetrate. The Voyagers apparently encountered several of these holes before finally crossing the boundary entirely. Each time Voyager 1 hit a hole in the magnetic barrier, cosmic rays flooded in, causing the intensity spikes. When the spacecraft moved away from the hole, the intensity dropped again. This continued until the spacecraft finally crossed the heliopause permanently. Voyager 2's crossing 6 years later showed similar but not identical behaviour. The spacecraft also experienced cosmic ray variations before the final crossing. But the pattern was different. The boundary structure at Voyager 2's location had different properties than at Voyager 1's location. This tells us that the heliopause is not a smooth, uniform surface. It's corrugated, bumpy, with variations over scales of astronomical units to tens of astronomical units. The boundary between solar system and galaxy is messier than theoretical models suggested. The cosmic ray measurements also revealed unexpected variations in interstellar space itself. Once beyond the heliopause, cosmic ray intensity should be relatively constant, varying only slightly with distance. Instead, both Voyagers measure significant fluctuations over time. These fluctuations might reflect true variations in the galactic cosmic ray flux. Supernova remnants, the main sources of cosmic rays, are distributed unevenly throughout the galaxy. The cosmic ray intensity at any location might vary as the solar system passes through regions closer to or farther from recent supernova events. Alternatively, the fluctuations might indicate that the Voyagers are still influenced by the heliosphere. Even deep in interstellar space, they might be affected by large-scale magnetic structures connected to the Sun, structures that modulate cosmic ray access. One particularly intriguing discovery: the cosmic rays come preferentially from certain directions. In truly pristine interstellar space, far from any stellar influence, cosmic rays should arrive isotropically, equally from all directions. The Voyagers detect anisotropies, directional preferences that suggest the local magnetic field is channeling cosmic rays along preferred paths. This anisotropy varies with time and differs between Voyager 1 and Voyager 2. indicating it's a local phenomenon related to the nearby magnetic field structure. It's not a global galactic property, but a feature of our immediate interstellar neighbourhood. The cosmic ray composition also holds surprises. Most cosmic rays are protons, but a significant fraction are heavier: nuclei, helium, carbon, oxygen, iron. The ratio of different elements tells us about cosmic ray sources and how particles propagate through the galaxy. Voyager measurements show that heavy nuclei are slightly more abundant in the local interstellar medium than previous indirect measurements suggested. This might indicate that nearby supernova remnants produced an unusual mix of elements, or that the propagation of cosmic rays through the galaxy favours certain elements over others in ways we don't fully understand. There's also the mystery of low-energy cosmic rays. The Voyagers can detect cosmic rays down to relatively low energies, tens of millions of electron volts. At these energies, cosmic rays are more easily deflected by magnetic fields and lose energy through various interaction processes. The detected spectrum of low-energy cosmic rays doesn't match theoretical predictions perfectly. There are more low-energy particles than expected, suggesting either that sources produce more low-energy cosmic rays than we thought, or that these particles don't lose energy as quickly during galactic propagation as models predict. Solving these puzzles requires understanding both cosmic ray sources, where and how they're produced, and cosmic ray transport, how they move through the galaxy's magnetic field and interstellar medium. The Voyager measurements provide crucial data for both issues, but they're just 2 points in a vast galaxy. We need more measurements from different locations to build a complete picture. The cosmic ray data also affects our thinking about radiation hazards for interstellar travel. Any future mission to another star system must protect its crew from galactic cosmic rays. The dose rate in interstellar space is higher than in Earth orbit by factors of hundreds or thousands. Voyager measurements give us the first direct data on this radiation environment. The news isn't encouraging for unshielded astronauts. Cosmic ray intensities in local interstellar space would deliver dangerous radiation doses over the years-long journey to even the nearest stars. This doesn't make interstellar travel impossible, just more challenging. Adequate shielding can reduce doses to acceptable levels, though the required shield mass is substantial. Alternatively, faster propulsion systems that reduce travel time would reduce exposure duration. The cosmic ray anomaly, the unexpected variations, the directional preferences, the compositional quirks, reminds us that interstellar space is not the empty void we once imagined. It's filled with particles and fields, structured by magnetic forces, varying with position and time. The Voyagers have given us our first taste of this environment. What they've found is both familiar and strange, confirming some predictions while overturning others. As the spacecraft continue their journey, they'll continue refining our understanding of the cosmic ray environment in our galactic neighbourhood. In 2012, Voyager 1 detected something completely unexpected: sound. Not sound in the traditional sense. Space is a vacuum where sound waves can't propagate. But waves of pressure moving through the tenuous plasma of interstellar space, oscillations that would be heard as sound if the medium were dense enough to carry it to human ears. These plasma oscillations revealed themselves through Voyager's plasma wave instrument, designed to detect electric and magnetic field oscillations. As the spacecraft crossed into interstellar space, this instrument began picking up signals it had never encountered in the heliosphere. The waves occurred at specific frequencies determined by the density of the interstellar plasma. Electrons in the plasma oscillate at their natural frequency, called the plasma frequency, which depends only on how many electrons are present per unit volume. By measuring this frequency, scientists could determine the exact density of interstellar space around the spacecraft. What they found was surprising. Interstellar space near the heliopause is denser than models predicted. The plasma density is about 40 times higher than in the outer heliosheath, the region just inside the heliopause. This is a far more dramatic transition than expected. The high density suggests that interstellar material is compressed near the heliopause, piling up as the solar wind pushes against it. This compression creates the enhanced density the Voyagers measured, making interstellar space near the boundary different from interstellar space farther away. But density isn't the only story the plasma waves tell. They also reveal something about temperature. Plasma oscillations are damped by particle collisions, and other processes that depend on temperature. By measuring how quickly oscillations decay, scientists can estimate the plasma temperature. The temperature measurements were shocking. Interstellar plasma near the heliopause is remarkably hot, thousands of degrees Celsius. Not hot in the way we think of it on Earth. The plasma is so tenuous that it contains almost no thermal energy despite the high temperature, but hot enough to tell us that something energetic is happening at the boundary. This heating might come from shockwaves or magnetic reconnection occurring at the heliopause. When the supersonic solar wind slams into the interstellar medium, it creates shockwaves that heat the plasma. When magnetic fields from the Sun and galaxy reconnect, they release energy that also heats the surrounding medium. The combination of high density and high temperature creates interesting physics. The plasma pressure, density times temperature, is much higher in interstellar space near the heliopause than the solar wind pressure in the Helios heath. This pressure difference helps hold the heliopause in place, preventing the solar wind from pushing farther outward. The plasma wave detections weren't continuous. They occurred in episodes, bursts of oscillations lasting weeks to months, with quiet periods in between. This episodic nature suggests that something triggers the oscillations, exciting them above the background level where Voyager's instruments can detect them. One trigger appears to be solar activity. When the Sun emits a particularly strong burst of solar wind, a coronal mass ejection or other eruption, this disturbance propagates outward through the heliosphere. When it reaches the heliopause, it creates a ripple, a pulse of pressure that disturbs the interstellar plasma beyond. These disturbances travel as waves through the interstellar medium, and Voyager detects them as they pass by. By tracking when eruptions occur on the Sun and when oscillations are detected at Voyager, scientists can measure how fast disturbances propagate through the heliosphere and into interstellar space. The measurements reveal propagation speeds of thousands of kilometers per second, much faster than the solar wind itself. These are shockwaves racing ahead of the ejected material, analogous to sonic booms from supersonic aircraft. The fact that Voyager can detect solar disturbances even after crossing into interstellar space demonstrates that the heliopause is not a perfect barrier. Solar activity affects the interstellar environment beyond. The Sun's influence extends farther than the formal boundary suggests. Another trigger for plasma oscillations might be instabilities in the interstellar medium itself. Plasma is subject to various instabilities that can spontaneously generate waves. If conditions are right, oscillations can grow from small fluctuations, amplifying until they're detectable by Voyager. These spontaneous oscillations would tell us about the physical state of the local interstellar medium, the fact that we observe. Oscillations at all means the plasma is not perfectly calm, but contains energy that can drive wave motion. The sound of interstellar space has another peculiar feature. It changes over time. The frequency of oscillations varies, indicating that plasma density is changing as the Voyager moves through different regions or as the interstellar medium itself evolves. Over the years since crossing the heliopause, Voyager 1 has measured density variations of tens of percent. These aren't random fluctuations but seem to follow patterns, possibly indicating that the spacecraft is passing through structured regions of the interstellar medium. One possibility is that these density variations reflect the edge effects of the hydrogen wall discussed earlier. As Voyager approaches the wall, density should increase. The measured density changes might be early signs of this approach, though Voyager is still too far away to confirm this definitively. Alternatively, the variations might reflect natural turbulence in the interstellar medium. Like Earth's atmosphere contains eddies and currents, the interstellar medium might have similar structures on much larger scales. Voyager would detect these as density variations as it flies through. The plasma wave measurements also revealed something about the magnetic field that other instruments couldn't determine. Plasma oscillations depend on both density and magnetic field strength. By combining plasma wave data with magnetometer measurements, scientists could determine the field strength more accurately than with either instrument alone. This combined analysis confirmed that the interstellar magnetic field is stronger than many models predicted. The field strength is several microgauss, significantly higher than the few microgauss typical of the general interstellar medium. This strong field suggests we're in a somewhat unusual region of local interstellar space, perhaps near the boundary of a superbubble or other large-scale structure. The sound data has practical implications for understanding how signals propagate through interstellar space. Any future communication with interstellar probes will have to account for the plasma environment. Plasma oscillations can affect radio wave propagation, potentially causing signal distortion or scattering. Knowing the density and temperature of interstellar plasma helps us design communication systems that can work in this environment. It's a small but important step toward the technology we'll need for future interstellar missions. The discovery that interstellar space has a sound, that you could theoretically hear waves propagating through the medium if you had sensitive enough equipment, captures the imagination. It transforms interstellar space from an abstract concept into something almost tangible, a place with physical properties we can measure and understand. NASA actually converted the plasma wave frequencies into audible sound waves, compressing the timescale and shifting the frequency into the range human ears can detect. The result is an eerie, otherworldly tone, the literal sound of interstellar space translated into something we can hear. This sound will change as Voyager continues its journey. The frequency will vary as density changes. New tones might emerge as the spacecraft encounters different regions. The symphony of interstellar space will continue playing, and Voyager will continue recording it for as long as the spacecraft survives. When the power finally runs out and Voyager falls silent, we'll lose this unique data stream. No other spacecraft currently in operation will reach interstellar space for decades. The sound of the cosmos beyond our solar system will become a memory, preserved in archived data, until the next generation of interstellar explorers eventually follows the Voyagers into the galactic night. Among the most puzzling discoveries from Voyager's journey into interstellar space is the detection of unexpected particle populations. These aren't the familiar solar wind particles or the predicted galactic cosmic rays. They're something else, particles with energies and compositions that don't fit our models of either the heliosphere or the local interstellar medium. The first hints came from Voyager 1's low-energy charged particle instrument, designed to detect ions and electrons in a specific energy range. As the spacecraft approached and crossed the heliopause, this instrument detected bursts of particles with anomalous properties. These particles appeared to originate neither from the Sun nor from typical galactic sources. Their energy spectrum was wrong for solar wind. Their composition was wrong for galactic cosmic rays. They seemed to be accelerated locally, somewhere near the heliopause, to moderate energies by some unknown process. Scientists initially suspected these might be pickup ions, atoms from the interstellar medium that become ionized and then accelerated by the solar wind. This is a known process that occurs throughout the heliosphere. Neutral atoms from interstellar space drift into the solar system, become ionized by solar ultraviolet light, or charge exchange, and then get swept up by the solar wind's magnetic field. But the energy distribution didn't match standard pickup ion predictions. These particles were too energetic, and they appeared in bursts rather than continuously. Something else was accelerating them beyond the typical pickup process. One possibility: magnetic reconnection at the heliopause. When magnetic field lines from the Sun and galaxy break and reconnect, they can release enormous energy. This energy goes into accelerating nearby particles, creating populations with unusual properties. If reconnection occurs in bursts, it would explain the episodic nature of the detections. Each reconnection event would accelerate a batch of particles, which Voyager would detect as a burst. Between events, the flux would drop to low levels. This explanation requires that reconnection occur frequently near the heliopause, which fits with the magnetic field measurements, suggesting that solar and interstellar fields are indeed interacting strongly at the boundary. Another mystery involves particles travelling in unexpected directions. Some of the detected particles were moving outward from the Sun, as expected for particles accelerated in the heliosphere. But others were moving inward, back toward the Sun, as if they had been accelerated somewhere beyond Voyager and were now falling back toward the solar system. This inward moving population is particularly puzzling. What could accelerate particles in interstellar space and send them toward the heliosphere? One possibility is that shockwaves from nearby supernova remnants are propagating through the local interstellar medium, and Voyager is detecting particles accelerated by these distant shocks. The timescales match. Supernovae occur in our galactic neighbourhood every few thousand years. Shock waves from these events propagate through interstellar space at speeds of hundreds to thousands of kilometers per second, taking thousands of years to cross the distances to our solar system. If Voyager is encountering the remains of shocks from supernovae that exploded thousands of years ago, it would detect particles with exactly the properties observed: moderate energies, unusual compositions, and trajectories that don't correlate with solar activity. Testing this hypothesis requires looking at the composition of the anomalous particles in detail. Supernova remnants produce specific, isotopic signatures, enrichment in certain heavy elements that are created in the explosion. If the anomalous particles show these signatures, it would support the supernova explanation. Unfortunately, Voyager's instruments can't determine detailed composition for the low-intensity particle populations we're discussing. They can identify general categories: protons, helium nuclei, heavier ions, but not specific isotopes. More sensitive instruments would be needed to test the supernova hypothesis definitively. There's also a population of electrons behaving strangely. Electrons are much lighter than ions and respond differently to magnetic fields and electric fields. They should be confined more efficiently by magnetic field lines, trapped in regions where field strength is high. But Voyager detects electrons in places where they shouldn't be able to reach based on standard magnetic confinement theory. They appear to be escaping from regions where they should be trapped, or entering regions that should exclude them. This suggests that the magnetic field structure near the heliopause is more complex than our models represent. There might be field-aligned currents, regions where electric fields accelerate particles along magnetic field lines. Or there might be intermittent connections between different field regions that allow particles to leak through barriers that should confine them. Understanding these particle populations is crucial for understanding the physics at the heliopause. Particles carry energy and momentum. Their motions affect the pressure balance that determines where the heliopause sits. If we can't explain where these particles come from and how they're accelerated, we're missing something important about how the boundary works. The unexpected particles also have implications for energetic particle events that affect Earth. When the Sun emits a powerful solar storm, energetic particles from that storm can reach Earth within hours or days, creating hazards for satellites and power grids. But some energetic particle events at Earth don't correlate with solar activity. They seem to come from elsewhere, possibly from interstellar space. The Voyager detections suggest that the local interstellar medium is more active than we realized, potentially contributing to the energetic particle environment throughout the heliosphere. If particles are being accelerated at the heliopause or in nearby interstellar space, some of those particles will diffuse inward toward the inner solar system. They'll add to the background radiation environment, creating hazards that have nothing to do with solar activity and thus can't be predicted by monitoring the Sun. This complicates space weather forecasting. We've been assuming that most hazardous energetic particles come from the Sun, so monitoring solar activity gives us warning of incoming threats. But if a significant fraction comes from the heliopause or beyond, we can't predict it by watching the Sun. We need dedicated sensors at large distances to provide warning. The unexpected particle discoveries have spawned a cottage industry of theoretical papers trying to explain the observations. Every major space physics conference now features sessions on heliospheric boundary phenomena, where researchers present models of particle acceleration, magnetic reconnection, and shockwave interactions. Some models are quite exotic, involving plasma instabilities that have never been observed directly, but are predicted theoretically. Others invoke well-known processes, but in configurations that are unusual or extreme. None of the models are fully satisfactory yet. They all explain some observations while struggling with others. The truth likely involves multiple processes occurring simultaneously, making the heliopause region a complex laboratory where many different acceleration mechanisms operate. What's clear is that the heliopause is not a quiet boundary where the solar wind simply peters out and interstellar space begins. It's an active, dynamic region where particles are being accelerated to high energies, where magnetic fields are reconfiguring, where shocks and waves propagate back and forth. This activity might be typical of stellar boundaries throughout the galaxy. Every star creates a heliosphere, and every heliosphere has a heliopause. If our heliopause is actively accelerating particles, others probably are too. This means that the galaxy is filled with regions around stars where particle acceleration occurs, contributing to the overall population of energetic particles throughout the galaxy. Understanding the processes at our heliopause helps us understand stellar winds and their interactions with the interstellar medium throughout the galaxy. The Voyagers are providing data relevant not just to our solar system, but to astrophysics more broadly. As the spacecraft continue their journey deeper into interstellar space, the particle detections will continue. The populations might change as the spacecraft leave the immediate vicinity of the heliopause and sample more pristine interstellar medium, or new populations might appear, revealing additional acceleration processes we haven't identified yet. Each new detection is a clue, a piece of the puzzle about how energy and matter flow through the boundary between stars and the galaxy they inhabit. The Voyager discoveries at the edge of the solar system aren't just abstract scientific findings. They have direct implications for Earth, for our technological civilization, and for our long-term future in space. Start with cosmic rays. The Voyager measurements of cosmic ray intensity in interstellar space tell us what radiation environment Earth would experience without the Sun's protective heliosphere. The flux is dramatically higher than what reaches Earth's orbit, higher by factors of hundreds in some energy ranges. This radiation has shaped Earth's environment throughout history. Cosmic rays entering the atmosphere create cascades of secondary particles, some of which reach the surface. These particles cause mutations in DNA, potentially driving evolutionary change. They affect cloud formation, possibly influencing climate. They create isotopes like carbon-14 that we use for radiocarbon dating. But Earth's atmosphere shields us from most cosmic ray effects. The thick layer of air absorbs most particles before they reach the surface. Only the highest energy cosmic rays, and their secondary products, make it through in significant numbers. However, the cosmic ray flux isn't constant over time. The Voyager data, combined with historical records from ice cores and tree rings, shows that cosmic ray intensity varies on multiple timescales. Solar activity modulates the flux on 11-year cycles. The solar system's motion through the galaxy creates longer-term variations as we pass through regions of different density and magnetic field strength. Some researchers have proposed that these variations might have affected Earth's climate over millions of years. When cosmic ray flux increases, cloud cover might increase, cooling the planet. When it decreases, cooling reduces. The effect is controversial and difficult to prove, but it's plausible. The Voyager measurements help constrain these theories by providing ground truth about cosmic ray intensity in the local interstellar medium. We now know what the baseline flux is, against which historical variations can be measured. The discoveries also affect our understanding of space weather. We've always known that solar storms can disrupt satellites, power grids, and communications. But the Voyager findings suggest that the interstellar environment also matters. The heliopause moves, it oscillates with the solar cycle, and it might undergo larger excursions in response to unusual events in the local interstellar medium. If a particularly dense cloud of interstellar material encounters the solar system, the heliopause could be pushed inward dramatically. This would expose the inner solar system to higher cosmic ray fluxes and to direct contact with interstellar particles. The radiation environment around Earth would change, potentially affecting satellite operations. The upper atmosphere would interact with interstellar material, possibly creating unusual atmospheric effects. Such an event might be rare, occurring only once every few million years, but it's not impossible. The solar system moves through a variable galactic environment, and eventually will encounter unusual conditions. The Voyager data gives us a baseline to compare against. If we monitor cosmic ray intensity and particle populations over decades, we might be able to detect changes that signal an approaching dense cloud or other interstellar feature. This would give us warning to prepare, protecting critical infrastructure, and understanding what's coming. The magnetic field measurements have implications too. If the local interstellar magnetic field is stronger than typical galactic values, as Voyager suggests, then cosmic rays approaching from certain directions might be deflected more than from others. This creates an anisotropy in cosmic ray arrival directions, which we detect at Earth. Understanding this anisotropy helps us map the local magnetic field structure, which in turn tells us about our location in the galaxy. We're apparently in a region called the local bubble, a cavity blown out by ancient supernovae that's now filled with hot, thin plasma. The magnetic field measurements from Voyager help us understand how this bubble interacts with surrounding structures, giving us better context for our galactic neighbourhood. For future space exploration, the Voyager findings are sobering. Any mission to interstellar space must deal with the radiation environment the Voyagers have measured. Astronauts travelling beyond the heliopause would be exposed to cosmic ray doses far exceeding anything experienced in Earth orbit or even on the lunar surface. Adequate shielding is possible, but massive. Water, hydrogen-rich materials, or heavy metals can block cosmic rays, but you need thick layers to reduce doses to acceptable levels. This adds mass to any interstellar spacecraft, making propulsion more challenging. Alternatively, faster travel times reduce exposure duration. If you can reach another star system in years rather than centuries, astronauts receive less total dose. This creates incentives to develop advanced propulsion systems capable of reaching significant fractions of light speed. The Voyager discoveries also inform our search for life beyond Earth. The heliosphere shields the inner solar system from some galactic radiation and from direct contact with interstellar material. This might be important for the development and survival of life. If other stars have similar heliospheres, then planets in their inner systems are similarly shielded. But stars vary in their stellar wind strength and in the interstellar environments they occupy. Some might have weak heliospheres that provide little shielding. Others might have strong ones that shield more effectively than the Sun's. This variation might affect where life can develop and persist. Planets around stars with weak heliospheres might receive lethal doses of cosmic rays. Planets around stars with strong heliospheres might be better protected, giving life more opportunity to evolve. Understanding our own heliosphere's properties helps us think about these issues for other planetary systems. The Voyager measurements provide a template for what we might expect elsewhere. There's also a philosophical dimension to the Voyager discoveries. The spacecraft have crossed a boundary that no human-made object crossed before. They've entered a realm that is literally alien, not part of the solar system where humanity evolved, but part of the broader galaxy. This crossing is symbolic as much as scientific. It represents humanity's first physical presence in interstellar space, even if that presence is just two small robots carrying our messages and instruments. The data they send back connects us to that realm. We learn what interstellar space is like not through abstract theorizing, but through direct measurement. We touch the galaxy in a sense, through the Voyager's sensors. This connection matters for how we think about our place in the cosmos. We're not confined to one star system forever. We've already reached beyond it, if only robotically. And what the Voyagers have found is that interstellar space, while harsh and hostile to human life, is not utterly alien. It follows physical laws we understand. It contains structures we can measure and explain. The boundary between solar system and galaxy is not a wall separating fundamentally different realms. It's a transition zone where different processes dominate. But it's all part of the same physical universe governed by the same laws. This gives hope for future exploration. If we can understand the heliopause with spacecraft built using 1970s technology, imagine what we'll learn when we send missions designed with 21st century instruments and capabilities. The Voyagers were pioneers, showing us that the journey is possible and that the destination is accessible to scientific investigation. For Earth and its inhabitants, the Voyager discoveries mean that we live in a dynamic cosmic environment. The Sun shields us from the galaxy's harsher aspects, but that shield varies in strength and position. We're connected to the galaxy, affected by its magnetic fields and particle populations, moving through its varied environments. Understanding this connection helps us appreciate how Earth's environment is shaped by cosmic influences. It's not just solar activity that matters. The interstellar medium matters too, in subtle ways we're only beginning to appreciate. And as we contemplate our long-term future, the Voyager findings remind us that leaving the solar system is not impossible, just very difficult. The obstacles are physical, not metaphysical. With sufficient technology and determination, we can follow the Voyagers into interstellar space, perhaps someday establishing ourselves as a truly galactic civilization. The Voyagers are dying, slowly, gradually, but inevitably. Their power sources decay, producing less electricity each year. Systems fail as components wear out after decades of operation. The end is approaching, though no one can say exactly when. Current estimates suggest both spacecraft will fall silent sometime in the 2030s, roughly 50 to 60 years after launch. This is extraordinary longevity for machines designed when computers filled rooms and the internet didn't exist. The limiting factor is electrical power. Each Voyager carries 3 radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity. When launched, these generators produced about 470 watts. Today, they produce barely enough to run the remaining instruments and keep the spacecraft warm enough to function. NASA has been managing power carefully for years, shutting down heaters and non-essential systems to conserve electricity for the most critical instruments. They've turned off cameras. There's nothing to photograph in interstellar space. They've shut down some particle detectors. They've even turned off heaters in regions of the spacecraft that can tolerate cold. But there are limits to what can be shut down. The radio transmitter must stay on to send data back to Earth. The computers must run to control the spacecraft. Some heaters are essential to keep critical components from freezing. As power continues declining, difficult decisions will be made about which instruments to keep running and which to turn off. The cosmic ray detector or the magnetometer, the plasma wave instrument or the ultraviolet spectrometer. Each choice means preserving some data streams while losing others. Eventually, probably around 2036 for Voyager 2 and perhaps 2037 for Voyager 1, there won't be enough power to run even one instrument. The spacecraft will fall silent, their transmissions ceasing after 6 decades of continuous communication with Earth. When that happens, the Voyagers won't suddenly stop existing. They'll continue their journeys through interstellar space, coasting along their trajectories at constant speed. No friction exists in space to slow them. No gravity is strong enough to capture them. They'll drift through the galaxy for millions or billions of years. In about 40,000 years, Voyager 1 will pass within about 1 light-year of the star Gliese 445. It won't actually get close enough to be captured or significantly deflected. It will just pass through the outer regions of that star's heliosphere, if it has one, then continue onward. In about 300,000 years, Voyager 2 will pass similarly close to Sirius. Again, it will just cruise by, a silent derelict carrying a golden record that no one will ever play. Eventually, after millions or billions of years, one of the Voyagers might encounter another star system closely enough to be captured gravitationally or to suffer a collision with a planet, asteroid, or comet. Or they might simply drift through the galaxy indefinitely, never encountering anything substantial enough to affect their paths. The golden records they carry will survive much longer than the spacecraft themselves. Made of gold-plated copper, the records should remain playable for billions of years if protected from cosmic rays and micrometeor impacts by the spacecraft structure. These records contain sounds and images from Earth, greetings in multiple languages, music from various cultures, pictures of humans and our planet, diagrams explaining our location in the galaxy. They're messages to hypothetical alien civilizations that might someday encounter the Voyagers. The probability of anyone finding these messages is vanishingly small. Space is vast and the Voyagers are tiny. They could drift through the galaxy for the entire age of the universe without coming close to another inhabited world. But the gesture matters. We sent our messages into the cosmos not because we expected a response, but because it felt important to say that we existed, that we created art and music, that we wondered about the universe and reached out to explore it. The Voyagers represent humanity at our best: curious, ambitious, creative, willing to invest resources in projects that benefit not us, but distant futures. The spacecraft were designed and built by people who knew they would never see the interstellar phase of the mission. They worked on the Voyagers for the sake of discovery itself, for knowledge that would come decades after their own deaths. This long-term thinking is rare in human affairs. Most of what we do is aimed at immediate or near-term outcomes. The Voyagers remind us that we're capable of more, that we can undertake projects spanning generations for goals that transcend our individual lifetimes. Before the Voyagers fall silent, they'll continue sending back data from the frontier of interstellar space. Each year they travel farther from the heliopause, sampling new regions of the local interstellar medium. Each year they might discover new phenomena or see familiar phenomena change with distance. Scientists are particularly interested in watching for variations in cosmic ray intensity, magnetic field strength, and plasma density as the Voyagers move deeper into interstellar space. These measurements will tell us whether the unusual properties near the heliopause are localized to the boundary region or extend throughout local interstellar space. There's also hope that Voyager might detect the heliopause of another nearby star. If such a boundary exists within range, Voyager's instruments might detect changes in cosmic ray intensity or magnetic field direction that signal crossing into another star's heliosphere. This seems unlikely given the distances involved, but it's not impossible. Some nearby stars are closer than others, and if their heliospheres extend farther than the Sun's, Voyager might just reach one before running out of power. The data the Voyagers have already sent back will be analysed for decades. Each new theoretical development in plasma physics or astrophysics prompts scientists to revisit Voyager data with new questions. Observations that seemed unremarkable when first received might turn out to be crucial for testing new theories. In this sense, the Voyagers will continue contributing to science long after they fall silent. The data archive is permanent, available to future generations of scientists who will approach it with insights and questions we can't currently imagine. There are no immediate plans for a follow-up mission to interstellar space. No spacecraft currently in development is targeted toward the heliopause. The New Horizons probe, which flew past Pluto and recently passed Arakoth in the Kuiper Belt, is headed outward but lacks the instruments to make meaningful interstellar measurements. Future missions will likely wait for advances in propulsion technology. The Voyagers travel at about 17 kilometers per second relative to the Sun. This is fast by current standards, but still painfully slow for interstellar exploration. It took Voyager 135 years to reach the heliopause. A spacecraft travelling at a significant fraction of light speed could reach the heliopause in years rather than decades, and continue onward to nearby stars within a human lifetime. Such speeds require propulsion systems far beyond anything we currently have, but they're not impossible in principle. Nuclear fusion, antimatter, or laser-driven light sails might eventually enable such speeds. When that technology becomes available, whenever that might be, we'll send new explorers into interstellar space, equipped with modern instruments and capable of reaching distances that will forever remain beyond Voyager's grasp. Those future missions will build on what the Voyagers discovered. They'll target specific questions raised by Voyager data. They'll carry instruments designed to measure phenomena Voyager detected but couldn't fully characterize. The Voyagers are first-generation interstellar probes, pioneers whose discoveries will guide their successors. Like all pioneers, they're crude by the standards of what will follow, but they blazed the trail, showed us that the journey is possible, and revealed what awaits beyond our solar system's edge. When Voyager 1 and Voyager 2 finally fall silent, humanity will lose our only active connection to interstellar space. For a while, perhaps decades or longer, we'll have no functioning instruments beyond the heliopause. The frontier will be dark and silent from our perspective. But the Voyagers will still be out there, coasting through the galactic night, carrying their golden records, representing humanity in realms we cannot yet reach ourselves. They'll drift past stars we've never seen. They'll traverse regions of the galaxy we can barely imagine. They'll witness cosmic events we'll never know about. And through it all, they'll remain our ambassadors, our first emissaries to the cosmos beyond the Sun's embrace. The Voyager missions teach us that exploration is worth doing for its own sake, that knowledge matters even when it has no practical application, that reaching for the stars, literally not metaphorically, is a fundamentally human endeavour. What the Voyagers found at the edge of our solar system is that the edge is not an ending but a beginning, not a wall but a threshold. Beyond our cosmic home lies not emptiness but complexity, not silence but sound, not isolation but connection to the larger galaxy. And now we know what's out there, waiting for us when we're ready to follow.